With limits, we can also talk about what happens as the x value approaches infinity. So the way we're going to describe these, we're going to look at different sequences. So looking at individual terms, like plugging in 1, then 2, then 3, then 4, etc. Probably not going to plug in all those terms, especially if we're going to infinity. But we're essentially going to be looking at the limit as x, well, I guess it's technically n approaches infinity, of a sub n. So what happens as we get further and further along? So for this, we're just going to kind of practice this by plugging in some values. So we got a sub n equals 2 to the n plus 1, sorry, 2n plus 1 over n plus 4. Let's just start by finding the first term. So our first term, sorry, my screen got a little wonky. A sub n, a sub 1 equals, well, I'll just plug in 1. 2 times 1 plus 1 over 1 plus 4. Well, 2 times 1 is 2, plus 1 gives us 3, and our denominator is 5. So 3/5. Now, just for kicks, I'm going to put that as a decimal, even though I don't really care for decimals, whatever. Now, if we plug in a sub 2, we'll do 2 times 2 plus 1 over 2 plus 4, so just replacing the n's with 2. We end up with 5 over 6, which as a decimal is, oh goodness, I should have written this down ahead of time. It ends up being, sorry, divided by 6. I'm not good with my 6 fractions. Is, oh my goodness, I did that decimal yesterday. 0.83 repeated forever. Now, if we keep going, let's jump to like a sub 50. A sub 50, we can plug in 50. We got 2 times 50 plus 1 over 50 plus 4. Well, 2 times 50 is 100 plus 1 gives us 101 divided by 54. Now, if we type that in, we got 101 divided by 54 as a decimal. That's about, well, I'll round it. So we're going to say 1.87. Now, if we plug in 1,000, a sub 1,000, we're going to have 2 times 1,000 plus 1 over 1,000 plus 4. When we type that in, or when we simplify this, we got 2 times 1,000, which is 2,000. So plus 1 gives us 2,001 over 1,004. And as a decimal, let me type that in. Sorry, I didn't write these out ahead of time. That's about equal to 1.99. Now, as we go further and further and further, it's going to get closer and closer and closer to 2. It's never going to be quite exact. If you plug in 1,000,000, well, your calculator might freak out and say it's equal to 2, but that's just because it's rounding weird. So we're going to say the limit as n approaches infinity of 2n plus 1 over n plus 4 is equal to 2. It's going to approach 2. Now for the second example, it's very similar, but instead of 2n plus 1 over n plus 4, it's going to be 2n plus 1 over n squared plus 4. So we'll do the same type of deal. We're going to do b sub 1, because it's a different function. We got b sub 1 equals 2 times 1 plus 1 over 1 squared plus 4. Well, we actually did that numerator before. 2 times 1 is 2, plus 1 gives us 3. Denominator, 1 squared is 1, plus 4 gives us 5. So it's still 3/5. b sub 2. We got 2 times 2 plus 1 over 2 squared plus 4. So in the numerator, 2 times 2 is 4, plus 1 gives us 5. Denominator, we got 2 squared, which is 4, plus 4 gives us 8. So 5 over 8. I'm just going to jump to b sub 10. We got 2 times 10 plus 1 over 10 squared plus 4. Now, the numerator, we got 2 times 10 plus 1, that gives us 21. Our denominator, it's 100 plus 4, that's 104. If we type that in, so we got 21 divided by 104, we end up with about equal to 0.2. If I go, let's say, b sub 100, we're going to have 2 times 100 plus 1 over 100 squared plus 4. 2 times 100 plus 1 gives us 201. 100 squared is 10,000 plus 4 is 10,004. Now if we type that into a calculator, it's going to give us about 0.02. Now if we get further and further along, the decimals are going to get smaller and smaller. We're going to add more and more zeros. It's going to be getting closer and closer to 0. So we're going to say the limit as x approaches infinity, oh, sorry, not x, n approaches infinity, since we're doing a sequence, of 2n plus 1 over n squared plus 4 is equal to 0. Letter C, we're going to follow a similar pattern. We're just going to plug in a couple, and then after we do letter C, we're going to talk about some patterns we can observe. So, sorry, my computer's being fussy. So, plugging in, starting with C sub 1. So we'll do C sub 1 equals, well, now it's a little varied. We got 2n squared plus 1. So we got 2 times 1 squared plus 1 over 4 times n squared, in this case, 1 squared. Numerator, we got 2 times 1 squared, well, that's just 2. Plus 1 gives us 3. Denominator, we end up with just 4, which if you were to put that as a decimal, is 0.75. Let's just jump to C sub 10. So we got 2 times 10 squared, so 2 times 100 plus 1. That's going to give us 201 over 4 times 10 squared. So 4 times 100 giving us 400. Now as a decimal, that's about equal to 0.5025. It's a little bit rounded. Sorry, I just want to check something. Next, scratch that. It's not even rounded. I was like, wait a second. I had this on my answer key as rounded. It's not. It's exactly 0.5025. Now, C sub 100, going even bigger, we got 2 times 100 squared plus 1 over 4 times 100. Oop, not 10,000, sorry, 100 squared. So that gives us 20,001. Oop, too many zeros. Over 40,000. Now if we type that into a calculator, we end up with 0.50025. You'll notice we just keep adding more and more decimals. If we went to like 1,000, we'd add more decimals. If we went to 1,000,000, we'd add even more decimals. But at that first decimal place, you'll notice it's starting to be consistent already. So I'm going to say the limit as n approaches infinity of 2n squared plus 1 over 4n squared is getting closer and closer to just be 0.5, or as a fraction, 1/2. Now at the bottom of this page, I want to add a couple notes to kind of like shorten up our work for this. We don't need to type this in every time. So, limits at infinity are horizontal asymptotes. And here's how we can identify them. So, looking at our patterns here, if the degree of the numerator equals degree, degree of denominator, then the limit as n approaches infinity of, you got to kind of think about it as like two functions, f of n, or I guess we'll just use, I'll use f of n, over g of n is going to be equal to the leading coefficient divided by the leading coefficient. So taking a look at that last example we did, the degrees of 2n squared and 4n squared are equal. We got a 2, we got a 2. So what we could have done, instead of having to go through that whole pattern, is look at the leading coefficients. It would be 2 over 4, which, hey, look at that. It's 1/2. Now, if the degree I'm going to start abbreviating. So the degree of numerator is less than degree of denominator, the limit as n, or whatever variable you're using, approaches infinity of f of n over g of n approaches 0. We ran into that in the second problem. The degree of the numerator is less than the degree of the denominator. Finally, if the degree of the numerator is greater than the degree of the denominator, then we say the limit doesn't exist. So the limit as n approaches infinity of f of n, oops, sorry, I got what f of x, doesn't really make a difference if we're using x, f of n over g of n does not exist. And I'm going to use the letters D and E, does not exist.